sciences that we are organizing between ICTP and IIT Mumbai. This is the first colloquium after the summer break, and we are very pleased and honored to have Julia Yeomans as our speaker. So I pass the word to my colleague Mitu from IIT Mumbai.
Thank you, Edgar. It's a pleasure to, of course, have Professor Yeomans with us today. Professor Yeomans is, of course, well known for her seminal contributions to critical phenomena in statistical mechanics, her work on complex fluids, as well as in biological systems. She did her doctoral work at the University of Oxford on critical phenomena of disordered systems, and then moved on to a postdoctoral position with Michael Fisher at Cornell. She then joined the University of Southampton in 1981 and moved to the University of Oxford in 1983, where she has been a professor of physics since 2002, and she currently heads the Rudolf Peierls Center for Theoretical Physics at Oxford. Professor Yeomans has received multiple honors and awards throughout her career. Notable among these, she was elected a Fellow of the Royal Society in 2013 in recognition of her contributions to the development of novel numerical and analytical modeling tools to investigate a wide range of complex fluids. And most recently in 2021, she received the Sam Edwards Medal and Prize from the Institute of Physics for her contributions to soft and active matter, statistical physics, and biophysics. So I pass the stage to Professor Yeomans. Today she'll speak to us about modeling the dynamics of confluent cell layers. Professor Yeomans, please.
Okay, thank you very much. And thank you very much for the invitation. Good afternoon, everyone, and it's lovely to be able to talk to you. I'm just getting over COVID, so I'm a bit I tend to cough and be a bit hoarse, so hopefully it's going to be all right with my voice-wise. So sorry if I end up coughing too much. So a while since I've given an online seminar, actually, we're almost back to normal over here. So let's see if I can remember how it all works. I'm going to talk about modeling the dynamics of confluent cell layers, but let's start with active matter. Okay, hang on. Oh, that's it. That's the right one. Okay, so backwards, that's it. So what active matter is material which takes energy from its surroundings and uses it to do work. And so active systems are meant to be out of thermodynamic equilibrium. So for physicists, this is a lovely way of looking at non-equilibrium statistical physics. And in particular, to look at the behavior of collections of particles which are meant to exist without coming to thermal equilibrium. And a beautiful example of that is biology. With Schrödinger, many, many years ago, in his book, What is Life, said that living matter evades the decay to equilibrium. And increasingly, this is how we're thinking about, one way of thinking about biological systems. So this is a Drosophila embryo, and those little white dots are individual cells. And if we can get this movie to play, I think it flipped right to the end there. Oh dear. This was working beautifully a minute ago.
Yeah, it was playing just now.
Yeah, it was playing just now, wasn't it? Let's see if, I wonder why it's doing this. Nope, it's just flipping immediately to the end. Let me just see if the other movies are doing the same. That one's fine. Okay, so we're going to miss this one out. But what it's meant to show is that in these systems, flows and forces are important.
Maybe if you start the presentation once more, like escape and enter the presentation.
I can try that, yes. Let's escape and I can start. Yes, well done. Okay, so this is the Drosophila embryo growing into a grown-up fruit fly. And you can see that it's very complicated. But as well as biology in there, there's quite a lot of physics in there. There are flows which are helping this thing change shape. And we'll see that there's pattern formation and self-assembly. Somehow this thing knows how to form a very complicated structure. This is active matter. Because it's out of equilibrium, it's able to evolve and choose which structure it wants to come to. And one of the big questions in biology is how this sort of morphogenesis happens. This is too hard for us at the moment. So we're going to think about much simpler systems. And in particular, the first thing I'm going to worry about is a dense suspension of microswimmers. So again, active particles which are all together, now active particles which are much simpler. And what you find is if you put these things together, what you end up with is something called active turbulence, a state where you get a turbulent-like chaotic flow state, even though you're at low Reynolds number. So the first part of my talk is going to talk about things like that. And then I want to say, okay, so if I look at a confluent layer of epithelial cells, these are cells plated on a Petri dish, you end up with the same sort of active flows. Are the same things happening? Can we use the same sort of theories to describe suspensions of microswimmers and confluent cell layers? They're both dense suspensions of active particles. What's the difference between them? So I'll start talking about active pneumatics and motile topological defects. This is sort of background. This is now well known. And in a way, it's an introduction for those who aren't used to this area. Then I'm going to say, okay, what's the physics? How do confluent cell layers move? Can we write down a simple model, a physics sort of model, which gets the generic features of how confluent cell layers move? And does it have anything to do with active pneumatics and motile topological defects? I'll then talk about phase field. Hello. I'll talk about phase field models and see the different forces we can put in and what they do. And by then I'm looking at very sort of new research where we're not sure if it's right or not. I think what we found is interesting, but the jury is very much still out about the extent to which it describes what's actually happening in these cell layers. Please do please do ask questions if you would like to. Yeah, I said in the chat. Okay, so let's think about active pneumatics. So let me start by introducing the ideas of pneumatics. So pneumatic symmetry is if you have particles which have a special axis, but up-down symmetry. So there's no vector direction. Special axis, but the two ends of that axis are not distinguished. If you put together molecules or colloids which have this shape, they can form a pneumatic phase. A pneumatic phase which has a special direction up here, okay, pneumatic phase which has a special direction, but no long-range positional order. And what we're going to have to know about this phase is that one way of thinking about an order parameter is a director n, which tells me about this special direction. Another way of doing this is an order parameter q. I get the laser pointer, an order parameter q, which just essentially tells me the magnitude of this order, how aligned the things are, and also the direction. So q is just an order parameter which tells me whether or not I have a pneumatic phase. In these pneumatics, because of the symmetry, you can get things called topological defects. And in two-dimensional pneumatics, the important topological defects have topological charge plus a half and look like this, something like a comet, and topological charge minus a half, where they have this threefold symmetry. They're called topological defects because the distortion in the director field's trying to line up like this, but this defect distorts it, the distortion in the director field extends all the way to infinity. So these things actually have infinite elastic energy, and they couldn't exist on their own in an infinite system. They really only exist in finite systems or in pairs, in plus or minus a half pairs. And in an ordinary passive soft matter sort of pneumatic, these defects annihilate in pairs. They move towards each other and they annihilate to get back perfect pneumatic order. Don't worry too much about these equations, but I want to just write them down, because what I want to do is see how these equations change when I go from just an ordinary passive pneumatic to an active pneumatic. These are the equations of motion, the continuum equations for a pneumatic liquid crystal. You have, first of all, an equation for the order parameter Q. Q moves with the flow. It also rotates with the flow, because if you have one of these pneumatic molecules, what's going to happen is, because it's long and thin, if you have a shear flow, it's going to turn it like that. So you need to bung this in. And then you have a term which says in equilibrium, when the thing stopped flowing around, it relaxes to the minimum of a free energy, which is usually taken as a Landau-de Gennes free energy, just an expansion in the order parameter Q. Then you have an expression for the velocity. The way I've got it written here, it looks pretty much like the Navier-Stokes equations. An inertial term, which is usually small at these tiny length scales, is equal to the derivative of the stress tensor. And the stress tensor includes the usual viscous stress and also an elastic stress, which basically again says, because these things are long, thin molecules, as they move, they're going to induce a flow. But what we're looking at is an active pneumatic, like these bacteria swimming around. And so they're stirring the fluid, they're setting up extra flows. Those extra flows are going to give extra stresses, and we want to know how to add that extra term into the equations of motion. Well, I'm not going to do it in mathematical detail, but it's a nice symmetry argument about how you should do this. And to see how that works, let's think how one of these little microswimmers affects the fluid. This is a picture, an experimental picture of the far flow field around a swimmer. So you can see that a long way away, what this flow field looks like is that the swimmer pumps fluid out from its ends and pulls it in from the sides. And looking at that flow field, you can see that it has pneumatic symmetry. It has a special direction, but front and back are not distinguished from each other. And that's the sort of flow field you get round any active particle. And the reason is that they are active, they're self-propelled. And so there's no external force on them, which picks out a direction. What happens is that the forces have to be equal and opposite. So this thing moves by pushing the fluid with equal and opposite forces. And the resultant, if you do a multiple expansion, is a flow field like this. A pneumatic flow field has pneumatic symmetry. Let me introduce a couple of words of notation, which I'll use a lot later. And that's just the direction of the flow field. An extensile field pushes outwards along the direction of the director and pulls in along the sides. For those of you that might be used to swimmer language, that's often called a puller. A contractile flow field goes in the opposite direction. So stuff moves towards the ends of this pneumatic and then moves out.
Sorry, Julia, sorry to interrupt. There is a question from the audience.
Yeah, I just wanted to ask, so since the bacteria is like moving in one direction, is it not possible to have like a polar field? Is it necessarily always pneumatic? This fluid.
I mean, that's a really good question, and I quite understand why it's slightly strange. It's because what we're looking at here is the far flow field. Okay, what makes the swimmer decide it's actually going to have a direction to move in is the details of the near field. And the equations I'm going to write down are continuum equations, and so they pick up the far flow field.
I see.
Yeah. And you might worry about whether details matter, but what we find is that they actually don't when you're actually solving this thing.
Okay, thank you.
Yeah. Any other questions? No, so thank you. Questions are great because, and I'm sure, as you know, those of you that have done talks like this, you get a bit nervous about talking to a wall after a bit. So it's nice to know there are real people out there. Right, so we've got the swimmer making a flow field like this. The swimmers are all making flow fields like this. Let's add them up and see how that affects the equations of motion. And the answer is that you just need one extra term. It's an extra term which is an active stress, and it's a stress. It's equal to zeta q. Zeta is just a strength of the activity, how many swimmers you've got in there. And then this q is the order parameter. I haven't proved this, but it sort of makes sense on symmetry grounds that you need to describe the active stress in terms of Q because of the shape of that far flow field. This comes in the stress. It comes under a derivative. So what that means is that whenever you have a derivative in the order parameter, any sort of distortions in the pneumatic order, you're going to get stresses and therefore forces and therefore flows. And in a way, this is the punchline. Any gradients in the magnitude or direction of this pneumatic order parameter induce flow. That's why you get this active turbulence. What happens is that the pneumatic ordering is unstable to instabilities because of this active term. If you do a linear stability analysis, that comes out, but here's the pictorial version of that. If I start with a pneumatic state and there's a tiny fluctuation, bend fluctuation in this case, here the order parameter is changing from place to place. It has a gradient, so it will induce flows. You have to work out which direction those flows are, and it's in this direction like this, and you can see that that's just going to increase the bend, and eventually everything's going to go nonlinear, and you're going to go away from the pneumatic state. And where you end up, not obvious till you actually solve the equations numerically, where you end up is this active turbulence. It's turbulence-like flows. The picture up here is the velocity field. Active turbulence has these vortices and jets of velocity, localized jets of large velocity, which are yellow in this picture. And here's the vorticity field. You get these swirls, which we saw in the movie. These swirls are typically 5 to 10 bacteria in diameter. So the reds and the blues are regions of high vorticity. So this is active pneumatics, all right? So pneumatics are going to have these topological defects. What happens to the topological defects in one of these active systems? So the picture here shows a red dot whenever I have a +1/2 topological defect and a blue dot whenever I have a -1/2 topological defect. You can see them being moved around by the flows, and you can see them, if I manage to get the right ones, annihilating in pairs like they're meant to in a passive system. If you look up here, you can see the new thing, which is that they're created in pairs as well in the active systems. This makes a lot of sense because activity is pumping in energy. And so that's what gives you the energy so you can create these defects in pairs. If they were just created and just sat there, it wouldn't work because they'd annihilate each other very quickly. But the +1/2 defects are self-motile. In active systems, they move, and therefore they escape when they're created. Let me play that movie again while I'm explaining this. Here's a +1/2 defect. You can see that there's very obviously distortions in the directive field. Any gradients in the directive field give you stresses and give you flows. And just from the symmetry of this shape, you'll see that the flows are going to have a certain direction to them, and they're going to push this defect in one direction or another. The minus ones create flows as well because they have distortions, but because of the threefold symmetry, the flows balance. So they make flows, but they don't actually go anywhere. Here's a picture of the flow field. Around a +1/2, you get these two flow vortices. And extensile systems, the defects move towards their heads. And in contractile systems, they move towards their tails. And here is the sixfold symmetry of the flow field around this -1/2 defect. So this is just experiments. These are actually microtubule motor mixtures, but I don't really want to go into this. The green dots are the +1/2 defects, and here's a real system with the +1/2 defects being created. You can see the defect shapes here, the defect comet-like shapes. And down here is a time movie, what happens as a function of time. What happens is in this system, the microtubules get bent. You end up with a -1/2 defect here, which doesn't move. And here's the +1/2 defect, which moves away from the -1/2 defect. And although it doesn't look identical, things like the vorticity correlation function, things like the behavior of the defects are the same in this microtubule motor system and the same in the bacterial system. I'm Mithan, got a question?
So I just wanted to ask, so is there like a steady state number or density of these defects that depends on your activity or on the other parameters of the system?
That's right. The distance between the defects goes as the square root of k, where k is the elastic constant of the matic divided by the activity. So what I've got in this picture up here is basically a system which is better fed as you go from left to right. This is increasing activity, and for larger activity, you get more of these defects. And you get a steady state, yeah.
Okay. Thank you.
What we don't have is a theory of this. We understand it, we know what's going on, but we don't really have something that a theoretical physicist would call a theory of what's going on. We just understand from the simulations and the experiments the sort of thing that's happening. So here we are, here's the dense suspension of microswimmers, which I've played so many times. But is this going to be the same as these cell layers? So that's the question we want to ask now. And it's very much a physicist question. So in case I've got any biologists listening, this is the sort of disclaimer. I'm afraid we're going to do it like a physicist. We're going to try and look for generic properties of what's going on and see how far we get. And at the moment, it's very much a theory as well, but they're definitely experiments, which I think it's starting. I think we're starting to understand what the right experiments to try are. And also, before I start, I should say thank you very much to Guanming, who's done most of the work on this, and some of the early work I'm going to describe. I've been lucky enough to work with some excellent theoretical and experimental collaborators. So next I'm going to do the biology to the extent that I know any biology. I've been learning it over the last 2 years. And it's really complicated. But this is a physicist's view of biology. We're looking at two-dimensional layers of cells. This is very much a model system. You know, in the body, cells are three-dimensional. But for epithelial cells, it's perhaps not a too bad starting point, because epithelial cells form layers. They're the cells which line the organs of the body. For example, the skin is epithelial, or the lining of the stomach or the lungs is a layer of epithelial cells. You take them out and you grow them to confluence, i.e. there's no gaps between them. You watch what's happening. And what happens is that you get something which is definitely turbulent-like, and then it starts going around in a circle. Why on earth is it doing that? You know, this is not cells that just sit there. They actually move. We'd like to understand, can we model how they move? So let's start with the single cell. How does a single cell move? So this is looking down on the top of a single cell. Here's the nucleus. This green stuff is actin filaments, long, stiff polymers of actin. And then the red stuff is cytoplasm. How the cells move is that they grow these actin filaments. It's called treadmilling, and that pushes forward the front of the cell. The front of the cell then grabs the substrate with a focal adhesion and pulls itself forwards. If it just did that, it would just get longer and longer as it pulls itself forwards. So what happens is that then there's a contractile force which pulls in its tail, acts a bit like surface tension, but this is an active force, an active contractile force. And the biology behind that is a load of motor proteins, myosin round here, which pull on a network of actin fibers. And so for a physicist, this is how cells move, a polar driving, just a force pushing it forwards due to these actin filaments pushing it forwards. You're allowed to have an unbalanced polar force because it's got the surface to push on. That's why it's different from the swimmers. It can push on the surface. And then this self-contractile activity, remember contractile was something which moved inwards, which shrank the cell back to a circle, which is helping to keep it at a certain shape. And actually that's a pretty good physicist model of a single cell. These things do random walks, persistent random walks. And so a force which has a certain amount of noise on it is really quite a good way of explaining what's going on. That's single cells. Let's go back and ask how layers of cells move. Well, first of all, I've put this in the title, but I couldn't find a good picture because it's pretty boring when they do it, is the idea of cells jamming. Yeah, the question?
Yeah, yeah, Julia. So what do you mean by contractile for a cell? Like it's crawling on a substrate?
I mean the sort of forces that are acting on it. What happens is that around the outside of the cell, well, in the middle of the cell is something which creates forces, and the forces pull in the long axis and push out the side axis. So you're quite right that it's not contractile in terms of flows, but in terms of pattern of forces. This is what I call contractile, yeah? This is the long axis of the cell, and the forces relative to that long axis look like this. But I mean, that's a really good...
These are the force vectors rather than flow vectors in some sense, like the force it's exerting on the substrate.
That's right. It's a self-induced force still, though. There's no force on the surface. So basically, it's an active elasticity is pulling it in, and the physics behind that is motors walking around on these actin networks. Yeah.
Okay.
I mean, that's a very good idea. We're not really talking about flows here, but we're still talking about contractile forces.
Okay, thanks.
Okay, so how do these, so now how do these work when you've got lots of cells? Well, first of all, you can just have a layer which is jammed. It wriggles around, but the cells don't move relative to each other. And I couldn't find a nice picture for that because it's not doing anything and it's a bit boring. But what else it can do is flocking. And flocking is when the cells all decide to move in the same direction. And an example of this is this egg chamber of Drosophila. The surrounding cells all move in the same direction. And the movie just shows that happening. So this is looking at the wall of this egg chamber. Nobody knows why this is the case, but this is what happens. And this other movie is essentially the same thing, where you're seeing the cells move round the egg chamber. So certainly flocking sometimes happens. The other thing these things can do is they can do something which looks very like active turbulence. So what's the evidence that this might be active turbulence? Well, this is a plot of the velocity field in one of these cell layers. And just like active turbulence, you see regions where you suddenly get large velocities and you get a lot of vorticity. If you plot the vorticity correlation function, it looks very similar in the cell layers, in the simulations, and in the swimmer experiments. So the velocity field looks the same as active turbulence. One of these is a simulation and one of them is cells, and I can't remember which is which. Yeah. Hi, yes, yeah, hi.
So just a question. So this active turbulence you find in vitro systems, is that right?
At the moment, yes. I think it's true, yeah, that it's found, and it's found at the moment in 2 dimensions. In the body, I think you probably have active flows, but they're much more likely to be organized active flows rather than this random active flow. So yeah, this is a model system essentially.
Okay, thank you.
If you put the cells in a channel, so they're confined within a channel, and you measure the velocity field, these cells start to move. They spontaneously start to move because of the activity that they're creating. And in particular, you end up with a shear flow. And people understand how active materials behave in a 2-dimensional channel. And if you match the velocity profile, it's absolutely a perfect match between what's happening in these channels and what's happening in the theories. And indeed, the experimentalists in this lovely paper looked at this geometry because to see if they could find what the theories predicted, and that's exactly what they did find. Similarly, here in the picture I have here, in the movie I have here, and you can get it to move, what happens is that these are confined cells, and if you confine active matter, it will start going round and round, essentially a confined version of the shear flow, and you see this. Okay, so this looks like active turbulence. What about the topological defects? Oh, sorry, got to do this one first. Sorry, first one comes next, right. What this is showing a crossover between active turbulence and flocking. These are some quite old experiments now, but again, very beautiful experiments. Here's a picture of the velocity field when the thing is doing active turbulence. The experimentalists from the group in Milan added RAB5A. No one's quite sure what that does, but it's thought to muck around with the cell-cell junctions. And these cells take off and start flocking. Okay, so this is a plot of the velocity as a function of time in the active turbulent layer, the mean velocity. And up here is what happens if you get flocking. And for a biological experiment, this difference is amazing. usually error bars overlap each other in biological experiments. So there's a big difference when you do something which is probably to do with the cell-cell junctions. The next slide shows a movie of the same thing. The one on the left is active turbulence, and one on the right is flocking. Very different behavior. Play that one again because it's a bit quick. There we go. And we'll come back to that when we try and think how to model this. So I'm trying to sell you this as an example of active turbulence. Yep. Hi, Pragya. Sorry.
Hi. So my question is, when there is a change from active turbulence to flocking, do you see a change in the shape of the cells, or do they remain the same? The nematics.
I don't think that was never measured.
Okay. Okay.
A very good question, but it was never measured as far as I'm aware. Would be a really nice thing to measure, actually.
Yeah.
Yeah.
Thank you.
Okay. Right. Some more questions, I think, which is great.
Sorry.
Yeah.
Hi, Julia. I had a quick question. So this transition from an active turbulent behavior to a flocking behavior, so what was changed in the experiment? Was it discussed that led to this change? Or
They added this chemical, RAB5A.
okay.
No one's quite sure what it does, except that it is thought to muck up the cell-cell junctions in some way.
Okay.
So all we know is that probably the cell-cell junctions have something to do with this, and I'll come back to that later.
Right. Thanks.
Right, so if it's active turbulence, there should be these motile topological defects. And to our surprise, we found that there were defects in these systems. This is an MDCK layer of cells. On average, the cells are isotropic. So why can I call them pneumatic? And the answer is that they are stretched, at least over some time scale. And so you can say that locally you can put an average pneumatic director on these cells. You get short range pneumatic order. So we did that. We chose about 3 by 3 layers of cells, and we put down what the average extension was. Not ideal, be better to do more averaging, but that's what we were able to do. And we saw how this changed in time. And we had very obvious topological defects, and they were moving motile topological defects, but they were moving towards their heads. Moving towards their heads means that this is an extensile layer, but everybody knows that cells are contractile, that they pull in their tails. The machinery makes them contractile. So we were confused. Just to say that other people have also found these in now many different cell layers. And this, I'm not sure this movie is, yes, it's going to work. These are topological defects in bronchial epithelial cells. Just to show you another example, which was rather cute, because I was quite surprised. Now, even the topological defects are meant to have something to do with cancer. They found topological defects in the mesothelium, which is an epithelial layer. I think my biology gives up then, it's an epithelial layer. But what happens is that the cancer cells in ovarian cancer have to go across this layer to metasize, to size. And these defects cause flows, local flows, which the authors claim make a difference. And I won't have time to go into it in detail, but there are now about 20 different systems where these topological defects have been found in cell layers. And in some cases, people have argued that they do have a biological relevance. But there's a problem. I'll say what the problem is again. The problem is that if we're going to make these things look pneumatic, we have to have extensile activity, because extensile activity takes the shell and pulls it out into a pneumatic shape. Whereas from all we know about cells, they're contractile. That's the mechanism inside them. And contractile activity will take the cells and push them back to a circular shape, and then they won't be pneumatic. So we were very confused by that. And then to make it worse, in a recent paper, Lakshmi Balasubramanian was the experimentalist who worked with us on this. Indeed, we worked with them on this, really. What they found was this, again, if they genetically modify cells to change the interaction between the cells, to change the cadherin adherens junction, the E-cadherin knockout, to change the junctions between the cells, the defects, which were happily being extensile and moving towards their head, turned round and started moving in the other direction. So they weakened the cell-cell junctions biologically, and it looked like the defects changed direction. So this is really a list of what we didn't understand and what we need to do if we want to try and model the dynamics of a confluent cell layer. We need a model which predicts the active turbulence, the jamming, and the flocking. We need to understand the shape of the cells. You know, why on earth do we end up with something which looks extensile, looks extended, even though we think that the contractile interactions will put it back to circular. And we like to see topological defects moving in both directions. So the model we decided to look at is a thing called a phase field model. This is really just a movie to show you what it's doing. And it is a physicist model of trying to understand what's happening in these cell layers. Each of those individual cells is described by a phase field, phi I, which takes a value 1 inside the cell and 0 outside the cell. This phi I evolves in the normal way and moves with a local velocity, and at the same time you get a relaxation to a minimum of the free energy. And then the force acting on this system, I should say the other way around, the velocity of this system depends on the force acting through some sort of friction. So I have an overdamped dynamics. If I just have a free energy, this force would be just a passive force, and I'd have a passive system, but I have active forces in there as well. I need to put in the active forces somehow. So let me describe, first of all, the passive forces. What do we put in the free energy? And basically, the free energy is just cooked up to give us something which looks like a load of cells. So we have a Carn-Hilliard term, and that just says, for each cell, my phase field is 1 inside the cell and 0 outside. We have a soft constraint on the cell area, which keeps the cells more or less the same area. And then we say we don't want these things to sit on top of each other, and so we don't allow them to overlap, but we do like their interfaces to be close to each other to form a confluent layer. And so we put in a term which favors cell-cell adhesion. And then the passive force just relaxes us to the minimum of that free energy. And if this was just a passive system, it would be like a load of two-dimensional bubbles. And equilibrium would just be identical hexagons if it can get there, but sometimes it would get stuck in some sort of metastable glassy state. So the reason for this choice is just sensible, really, that you end up with something looking like what you want it to look like. It really is no more than that. But that's not an active system. We need an active system. So let's work out how we put in the active forces. And let's just go back to remembering how individual cells move. And individual cells are pulled with a polar force. So let's just bung that in and see what happens. So each of my cells has a polar driving on it. To do that, I choose a direction, which I've called the polarization for each cell, and then I distribute the force over the cell. So wherever phi I is 1, the force has some strength alpha, and it's in the direction of the polarization. So all I've done there really is instead of defining a force, I've got to choose what the polarization is. And you could choose P to just be a Gaussian variable, so this just wriggles around at random. Or you could choose the polarization to align with the velocity of the cell, and there's always going to be some sort of noise as well. Or you could choose it to align with the long axis of the cell. And we do that, and we have some sort of time scale, and we choose the alignment time to be about the time the cell moves the cell diameter. So each of these cells has forces acting on it. What happens? And the answer is that we get a jam state very nicely. What I'm plotting here is just the position of the center of mass of the cells. So in the jam state, the cells don't go anywhere. And then we get a liquid state where the cells move around. That's good. We hope this is active turbulence. And then we do actually get a flocking state as well, but only if we align the polarization with the velocity. And if we have any active matter experts in the audience, this is essentially a V-check model, that if you align the direction, the force acting on these things with the velocity, so they all tend to have the same velocity, you're going to end up with a flocking state. So we're almost there, except if this liquid was active turbulence, we'd be okay. But we looked for topological defects, no. We looked for vorticity, no. We looked for strong velocity fluctuations, no. It was just behaving like an ordinary liquid. There was absolutely nothing that said that it was this active turbulence. So that didn't work. We just got an ordinary liquid. So how can we get active turbulence in this system? Well, we could add a dipolar force. We know that this is what you need in the continuum theory to get active turbulence. And it's fairly easy to put that in to the phase field model. We just define a Q-tensor in terms of a local director, the extended axis of the cell. We distribute it over each cell, and then we have some sort of interaction. And we can do that, and that's fine. And indeed, we do get active turbulence. We can see the topological defects if the force is extensile, because the extensile force extends the cells, so they're pneumatic, and then you can get active turbulence. But that really isn't right, because cells are not extensile. So what's going on? What are we missing? And we believe that probably what we're missing is that what we want is pneumatic forces between the cells. The cells pull on each other. Sorry, actually next, yeah. So what's the evidence for that? Well, if you're a biologist, you will have heard of something called contact inhibition of locomotion, which is probably almost a belief rather than experimental fact. But it looks like in these cell layers, you don't get the actin pushing the edges of the cells. It looks like the cells turn off their polar forces when they're in a layer. And that sort of makes sense, right? Because you don't want cells all pulling in different directions if they're stuck there in a layer, because if that happens, they're just wasting energy to go nowhere. So in these layers with active turbulence, there's not really much evidence of polar forces. We also saw in this nice experiments from Milan, where we saw the crossover between active turbulence and flocking, we saw that that crossover was something to do with the cell-cell junctions. So the cell-cell junctions are probably important. And sort of makes sense, doesn't it? That what's different about a cell-cell layer is the cell-cell junctions. And it's known that there's an actin layer around the outside of the cells. It's known that the cells make things called adherens junctions between them. They're active junctions between the cells, and the cells are always pulling on each other. So to model the dynamics of a cell layer, maybe we need active, well, we certainly need active interactions. These things are certainly active. Perhaps we need interactions between the cells, intercellular interactions. The cells are pulling on each other. Makes a lot of sense. It took us a long time to realize that, but I think it certainly makes sense to me. And we'd expect them to be contractile because that's what cells do. The cells are trying to pull themselves in when they pull. So we could put that in. That's easy enough. We just have the stress on cell I depending on the zeta q from cell J. What happens? Well, what happens is that the cells are actually extended. Even though we've got contractile interactions, the cells tend to be extended. And if the intercellular adhesion isn't too strong, you end up with instabilities, which give you active turbulence and which give you contractile topological defects. Here's the movie. I'm afraid it's not very nice graphics, so it doesn't look quite like cells, but you're getting these topological defects forming, and you're getting the cells tend to extend. So why on earth are contractile interactions behaving like effective extensile interactions and extending the cells? And the answer is that it's because they're between the cells. And this is the picture. And now if I can actually get a pen, let me see if I can get a pen to write. I'll be able to try and show you how it works. Okay, so here's my test cell. I'm trying to see what the forces on my test cell are due to its neighbors. This neighbor is contractile. So the forces it's exerting are inwards along its long axis and outwards perpendicular to the long axis. And so the forces it exerts on its neighbor are in this direction. If I use the same argument for all the surrounding cells, what I end up with is that the forces on my test cell look like this. And so the forces on the test cell are pulling outwards along the long axis and pushing inwards perpendicular to that. And so there's an effective extensile interaction due to the fact that the neighbors are being contractile from the junctions with the neighbors. So contractile intercellular interactions do give me active turbulence. The defects move towards the tail. And so we're halfway there. We've got a much more physical system. Contractile interactions are what you'd expect. And it's giving us active turbulence. Going to finish with just two little extra points on that. The first one is really a physics point, which is, okay, we know that physically it's extensile interactions are not what's happening, but we can easily put them in the code. What happens if I make these intercellular interactions extensile? And so really perhaps more for the experts here is, again, you get extensile active turbulence, but you end up with actually very small weak defects which don't last very long. And you end up with this sort of ordering. We've called it a capped line state. You tend to get lines of cells which are lined up in a nematic way, but then the surrounding cells seem to be lined up perpendicular. And the reason for that is that the effective interaction between the cells is one which tends to line them up perpendicular to each other. It ends up being frustrated. I mean, you can't on this sort of lattice have everything perpendicular to each other. So what happens is you get a frustrated system where half the cells are parallel and half of them are perpendicular. And if you look at the angle between the cells, in my contractile system, the one with contractile intercellular interactions, everything lines up in an almost nematic state. In the extensile system, you end up with a sort of bimodal distribution that half of them are aligned parallel to each other and the other half are aligned at 90 degrees to each other. The first time I saw that, I said, that's just like simulations of hard rods. I mean, down here you can see it. These are just simulations of active polar hard rods. Okay, and what you can see down here is that you tend to get this half nematic order, and then you get these perpendicular orderings. Don't understand why at all, but you see very much the same thing. If you map this onto a field theory, you do indeed get that you have an effective positive elasticity, which wants to line things perpendicular. That's tricky if you haven't sort of seen that before, but let's go back to the cells, right? Because we do have one more question to answer with the real cells, where we have contractile interactions, which was that when I showed you the experiments, we had some of the defects moving towards the tail, but the defects could move to the head as well. How can we make these defects change direction? And the answer is that if you take a contractile system and you put on anisotropic shape fluctuations, and that again is very, very physical. These cells fluctuate their shape like mad. And so if I make them fluctuate in a way that the magnitude of the fluctuations is different, parallel and perpendicular to the nematic axis, you can show quite easily that the activity is renormalized, it's changed, and in particular, it can change its sign. So more fluctuations, more spontaneous noise can cross you over from defects which have a velocity which is negative relative to their head direction to one which is very slightly positive. What I think we never looked at experimentally and what needs to be looked at experimentally is that, in fact, in these cell layers with fluctuations, the average defect velocity changes from just negative to just positive as you increase the fluctuations. But this is a huge wide distribution, and we should think in terms of distributions of defects. So this really is where we're up to. My conclusions are that active, contractile, intercellular interactions reproduce a lot of the physics of these cell layers. We also need to put in fluctuations, and if we do, we can explain active turbulence in these layers, we can explain topological defects that move towards the heads, and topological defects that move towards the tail. There are lots of experimental questions now. Can we see any of these ideas actually in experiments? And I think up to now, the experiments really haven't quite asked the questions which would test these ideas. So I don't know if they're going to end up being right or not, but I think they'd be nice to explore. So thank you very much for listening.
Thank you very much, Julia. I think we have a little bit of time for questions, if any. Yes, Pragya, please.
So I have a question that if the at the individual scale, they have a polar symmetry, do you see asters or vortices come about, or there are no experiments or simulations in which asters and vortices are seen? There are only declination defects.
In the cells, in these cell layers, I haven't seen asters. I mean, there are other systems where you get asters. For example, I think microtubules, which are moving along a bed of molecular motors. So it has been seen in other systems, but not these.
Thank you.
Hi, I just wanted to clarify the model that you had. So initially you said that the cells are moving as a polar entity. You have a and that along with the Big-Shake-like interactions give a flocking behavior.
Yes.
And then the dipolar contractile interactions were added on the top of these polar interactions? Or,
no, we actually turned off the polar interactions. And so we either looked at polar or dipolar. If we want to go back and see, I mean, one possibility is that when the cells start to flock, they are turning back the polar interactions. We wouldn't see flocking with dipolar interactions.
I see. So it would be like more like when the cells are flocking, maybe the polar interaction is more dominant, and when it becomes more turbulent, the other dipolar interactions becomes dominant. Maybe we can.
That's the way I think about it, but it's very much a hypothesis and rather than something anybody has proved.
Okay, thank you.
Barish, yeah.
Hi, thanks for the very nice talk, Julia. I had a question. I'm not sure how well it fits in this presentation, but do you know if there is any correlation that one can make of the intracellular properties, biological properties, with the activity or the overall migratory behavior of the cell? Is there something that's known that's relevant?
I mean, it's certainly known that these things are active. And I think everyone would agree that the things which are moving them around, making them jiggle are active. But I think mapping those onto a sort of physical model of forces is something which is very new and not really known about. Sorry, I'm not sure that was a good answer. Would you like to rephrase your question? I'm not sure I've got the right question.
No, I think that's probably, I suppose what I'm asking is, so for example, the cells which flock or the cells which are, when it goes from a turbulent to a flocking behavior, can one also make a simultaneous measurement of what's happening, let's say, of the intracellular viscosity? Is there a change? Is there any mapping of physical properties?
We're way away from doing things like that. People are just starting to look at a ring of cells, so just a ring rather than a blob, and those sometimes flock. And it looks like in those rings that they develop a polarization because the front and back of the cells are different.
Mm-hmm.
In particular, I think the cell-cell junctions are different from front and back of the cells, but it's really very early days, those sorts of ideas.
Thank you.
Yeah. So, hi, Julia. Again, thanks for a very nice talk. So, I'm just trying to understand. So, you said that this contractile intercellular interactions leads to this extensile forces on your test cell.
Yeah.
So I had two questions. So I understood that picture that you said, but the test cell itself has a contractile force field like any other cell. So there is a balance between the contractile forces of the cell itself versus the forces exerted by the neighboring cell. And you were saying that this neighboring cells in some sense wins out, which leads to this.
That's right. We actually turned off the interaction within a cell just so we could see what we were doing in these simulations. If you add it back, you're right, they essentially add each other. So you'd need stronger intercellular interactions. And I think that's okay because they're different physical mechanisms. The interaction within a single cell is molecular motors walking on the internal actin. The interaction between cells is essentially the activity of the cadherin, the cadherin adherence junctions. The junctions between cells are active, and there's a layer of actin around the edge of a cell, which is sort of doing that. So they're two different physical things going on. So there's no reason why they should be the same.
Like, is it possible to mutate one of these interactions, for example, the cadherin versus the other ones, to sort of tune the strengths and see whether it leads a transition from?
Well, in a way, that's what we were doing in the Nature Materials paper by knocking out cadherin adherence junctions. But this is all really new, these ideas, so no one's really thought about them in terms of experiments in this same way. You might argue, but again, I'm just sort of throwing out ideas rather than believing it, is that when a cell decides to turn off its polar forces, this contact inhibition of locomotion, at the same time it turns off its internal contractile forces because it doesn't need them anymore. It doesn't need to go back to its circular shape.
All right, and one final thing. So you were also saying, that these cell shapes are fluctuating, which does that mean that this, what we call as the long axis of the cell, is getting interchanged with what is the short axis? That is also possible, the fluctuation?
It's certainly possible, but the way
I'm just wondering whether the overall forces of the test cell, because of this contractile, by the neighboring cells, will get time averaged out because of the fluctuations. I don't know if it made sense.
Yes, I mean, the fluctuations are going to make a difference, but it doesn't actually, they're not really going to be big enough to completely change the extensility to a contractility, to change the direction.
I see. Okay.
It's actually what matters is actually the difference between the longitudinal and transverse fluctuations in terms of changing the sign of the activity. And I mean, certainly these cells are fluctuating like mad. It's reasonable that those two rates of fluctuation are different along and perpendicular to the pneumatic axis, but no one's ever measured it.
All right. Thank you.
Hi, Julia. Thanks for the nice talk. So I think the argument that you made in the end was that even if your cell is contractile along one axis, it's extensile in the perpendicular axis, right? So was that the idea?
Don't think so. Do you mean about the fluctuations or the picture of?
No, not the fluctuations. Even at single cell, if you just draw out the flow field or the force field, it's contractile along the long axis, but it's extensile along the perpendicular axis. And like you said, like cell contracts along one axis and its primary axis becomes the perpendicular one. And for that instance, it's an extensile system.
No, I don't. No, it's not that. I mean, you're quite right that in a way, what counts as extensile and contractile is how you define the director. But it's not that. It's that when you have the neighbors pushing a cell, the cell that gets pushed actually ends up extending along its long axis.
I see.
So there's an effective extensile interaction due to neighbors.
Okay. I'll think about it, but that's a nice thing too. Yeah. And if you switch, okay, so if you start with a cell which is extensile to begin with, right? So do you get the merging behavior which is contractile?
I mean, the cells are always contractile.
No, I'm saying like hypothetically, if you have an extensile.
Sorry, yeah, okay. Hypothetically, if a cell was extensile, you would get extensile active turbulence, both from the interactions between the cells and
I see.
cells. Yeah.
Okay. Okay, thanks.
Shall I say who's on my list next? Sidipto?
Thank you, Julia, for a wonderful talk. I just wanted to clarify more about this contact inhibition locomotion, that how exactly it manifests in terms of these equations, and is it essential for this transition from this flocking state to this turbulent state? How exactly it plays out in terms of?
In our model, you would need the dipolar interactions to dominate to get active turbulence, and you need the polar interactions, the forces, to dominate to get flocking.
Okay.
And I mean, what people, you don't, you know, these things, when the actin pushes forward to move a cell, you get lamellipodia forming, sort of arms in the cell. And those are not seen. I mean, occasionally they're seen, but they're seen much less in cell layers.
Okay. Okay, thank you.
Yeah. Dipendu?
Yeah, so I was trying to understand these, flocking state. So when you say flocking, it's like global polar order that you are talking about, right?
Yes.
So, I mean, going back to sort of agent-based models, I mean, one knows that, you know, if you have these disks with some interaction and they are self-propelled, they don't lead to, for example, any global polar order until and unless you start putting also these alignment interactions like in Vichek. And similarly for the rods also, there has been a lot of models which, I mean, if they are rods and self-propelled, then they don't actually produce polar order. I mean, because they can easily move in two directions. And so I'm a little bit, because in this, all the things that you described, there were these rods, like particles, the pneumatics, as well as and they were self-propelled, and they were developing also in certain circumstances this global polar order. So is it like maybe, you know, this was the impression that I had, that you require something else to produce this polar order, and at least in models you put these alignment interactions, looking at the neighbors and then the majority rule kind of movement and all that. So am I incorrect in that, or what's?
No, you're right. We only get polar order if we align the polarization to the velocity, and that is essentially a Vichek-like interaction. So, if we align the polarization to the shape, we don't get flocking.
So this is where, you know, I'm again, perhaps this someone asked during the talk that there was some chemical added to the cells and it went from active turbulence to this flocking state. So, I mean, what do you think is going on microscopically? I mean, at the cellular level?
Okay, so a possibility, I mean, I have to be really careful because there's no actual evidence for this, but a possibility that it's worth testing, I think, is that if you start with active turbulence, the dipolar interactions between the cells are dominant. There's absolutely no polar forces at all. When you add this Rab5A, it mucks up the junctions between the cells. So it mucks up the contact inhibition of locomotion, and the cells turn on their polar forces again. So now they have polar forces, but then you have to have something extra, you're quite right, to get flocking. And what you need is that these polar forces tend to align to the velocity of the cells. So basically the cells have a persistent velocity, which somehow through the cell-cell junctions, they tell the neighbors around, right? So they all have a persistent velocity and they're pulling each other through the cell-cell junctions. That works in the models. That is not a biological mechanism, but there could be a biological mechanism for that.
Okay, thank you.
Yeah, Aditya?
Hello, Julia. It was a nice talk. I sort of had a very technical question. when we are modeling the contractile forces, do we also model certain constraints on the size of the cell as to how thin the short axis of the cell can be?
Yes, yes. Essentially, the passive forces which have a size constraint on the cell will do that for you. So it's very hard for these things to get very, very long and thin.
We would specify those separately during the modeling process.
So I didn't hear that because of the internet.
So we would have to specify these constraints separately during the modeling process. Would that
That's
be
right.
part of in the agent-based system we have made?
Well, it's constrained by the free energy. You do have a free energy. So even if this was a passive system, it would relax to a cell-like layer. So that's in the passive forces we've got. For example, we've got an effective surface tension in there from the phase field model.
Yeah.
Which makes sense. You kill a cell and it still sort of has a reasonably cell-like shape.
Mm.
Hi, Dibyendu?
Devendra, did you have another question, or is this?
Yeah, just a brief, just a brief question. So you have been calling this as a like a turbulence, active turbulence. So is there like quantitative comparison with like the velocity correlations or energy flows like with turbulence in a proper sense, or is it like a loose usage?
It's a loose usage. Inertial turbulence is very different because obviously it's high Reynolds number and the energy is pumped in at large length scales, whereas here you pump in the energy at small length scales. So I'm afraid it was a use of the word that someone in the street would use rather than a turbulence expert.
So here the velocity correlations, they die out within a short length scale, no? I mean, in the cell layers, I mean, how?
So, yes, that's another interesting question. In the bacterial system, probably the hydrodynamics is not damped, whereas in the cell layers, there's strong damping, strong friction. And I don't think we totally understand what difference that makes.
Okay, thank you. Yeah.
All right, I think that's the last of the question. Thanks a lot, Julia, for taking so much time to answer the questions.
Okay, my questions. Thanks very much.
Thank you, and hopefully, you can come and visit sometime and give another talk in person. Thank you. Thanks again.
I'm meant to be coming to India just when the pandemic started, so maybe I'll get there eventually.
Thank you.
Great.
Thank you, Julia.
Nice talking.
Thank you very much.
Bye. Bye.
Bye.
Bye.
Bye-bye.